Hi there. I want to do something a bit different today, which is to try to take you down the rabbit hole of mathematics with me. I have had a sort of journey, a math journey, as nerdy as that sounds. And I would be remiss if I didn't talk about it directly on this channel. I suppose I've talked about it indirectly because there's lots of math videos up, but I've never spoken about it in the way I'm going to talk about it today, which is as a story, as a journey. So I will try to take you down the rabbit hole with me, so to speak. You know, that's sort of a funny terminology. What the Alice in Wonderland author was a mathematician, right? Was an Oxford mathematician? My mother, I guess, thought about doing math, but she said she didn't do it. She didn't go in that direction because she was afraid she might go crazy or something like that, right? Like there's this image of mathematicians as going crazy or something like that, or physicists, the mad scientist, right? But yeah, I mean, I don't. By the end of this video, I hope you'll have some understanding of what I'm talking about. I'm trying to make this approachable. If you've done some high school math, and particularly, I'm going to start at some point talking about imaginary numbers, and then we'll take off from there. So if you have never heard of imaginary numbers, then this might be difficult for you. There's, I don't know, there's a Veritasium video about it, I think. Leave a comment if you need help. But yeah, so I had this journey, and I don't want to make this about me. I want it to be about the math. So I'm not going to talk about all the nitty-gritty details of my life. But yeah, I went through this journey basically where this sort of fire was ignited within me that sort of rekindled this a passion, I suppose. I mean, I was I was said to be quite gifted at math in school, but I didn't really do anything direct with it after high school. Anyway, so at some point this fire was relit, and I want to talk about that. And in fact, it started with physics, but I'm going to, we're going to talk about physics. This is physics and math. And so what I want to share, the reason I want to share this partly is because I think a lot of people have had an experience of wonder. For example, perhaps looking up at the stars, or perhaps looking through a microscope. Looking through a telescope at Jupiter, something like that. But, and it happens with math as well. A person who studies math might have a few of these moments in their life where they have this, maybe a realization, but this sense of wonder. And now, when I start thinking about math for even 5 minutes, I get that sense of wonder. And so I want to try to share that somehow, even though it might be difficult to do so. So we were going to start the talk with imaginary numbers, because we got to start somewhere. And actually, that's a good starting place, because, well, they're mysterious, aren't they? I mean, magnets, how do they work? Well, some people will tell you they're not mysterious at all. They're very simple. They do rotations and stuff, and there's nothing mysterious about it. I think that's wrong. Partly, well, we'll get into the larger context, okay? Because this is just the tip of the iceberg of a larger context in several ways. And so to defend that case that they are, imaginary numbers are a bit mysterious, the imaginary number I appears in the Schrödinger equation. If you don't know, Schrödinger equation is so quantum physics is going to come up here, and That was, I don't know if it's exactly the beginning of quantum physics, but it's close to it. The first time we sort of had an equation of what, for example, an electron is really doing. And the imaginary number I appears in that equation. So let's go back a step and talk about why imaginary numbers. And I also want to mention that mathematicians struggled with this, with imaginary numbers, for a couple hundred years. Now, some people have said that the name is unfortunate. I don't really care about the semantics of it. If the name, there's a better name, because imaginary makes students throw up their hands and say, we're never going to use this. And most people are never going to use it, unless if you go into engineering or physics, math, then you might use it. And actually, they're very useful. We'll get into that. But the way that I would explain it to a student would be that essentially you need this imaginary number I if you're going to ever talk about concepts of negative area. Now, usually in the world of complex numbers, so a complex number is an imaginary. It's the world of imaginary numbers plus the world of real numbers together. We call that the complex numbers. So, so usually in that conversation, we're not talking about negative areas necessarily, but that is sort of what it applies. The imaginary number I squares to the number -1. So you can think of that as a negative area. So, obviously positive and negative numbers are useful. If you were trying to make a budget and you represent debt as negative numbers, or outflow as cash outflow as negative numbers, etc. Or if you're talking about altitude, you got to pick somewhere as your zero altitude, and then you can talk about above sea level, below sea level, etc. Maybe with temperature, I don't know. But yeah, so positive and negative numbers are useful, clearly. Though you can point at it and say, well, what does it really mean? Because if you have -5 apples, what does that mean? Well, you could have a debt of 5 apples. I don't know. But so if you think that positive and negative, having negative numbers is useful, then why not for area? And, well, if you start having negative area, you need something that squares to a negative number. And so that would be my explanation to a student. But this is sort of ad hoc. In other words, we've seen, I'm looking at the tremendous usefulness of complex numbers, and then after the fact, I'm coming up with some kind of rationalization. Okay? But it is what it is. Now, so those who study it, you'll find that the complex numbers, basically, it's a very useful mathematical package that encodes scaling and rotation. Okay, so you might hear me say that a few times because it's really important. It basically encodes scaling and rotation. And so because of that, that by itself makes it so that it's not super surprising that complex numbers are very useful in engineering and things like electromagnetism. This idea that you have any time you have some kind of rotation, potentially, it's already super useful. Just having rotation. It's a nice, neat way to package rotation, but also scaling as well. Okay, so it's useful, but then you have it in the Schrödinger equation. That's sort of mysterious, and it is mysterious. And you can find videos if you look on YouTube for you search for, say, imaginary numbers physics. Okay, you'll get there's a lot of videos out there talking about why there's the number I in the Schrödinger equation. That's the main example, okay? But you find a lot of videos about that, and it's an interesting topic, and it's worth reading about. It's worth thinking about. I don't think it's just cut and dry, totally 100% trivially solved, and like, oh, why are you even asking that question? Well, duh. It's some people might act that way, but I don't think that that's the case. I think that it's. I like to think that it's a bit mysterious. I do. Now you can sort of wave things away by saying, well, the imaginary number I is useful because it encodes rotation. Okay. But moving on, then there was this sort of revolution in math and physics that is not, well, it is talked about a bit, but not nearly as much as it should be. It's not nearly as well known as it should be. And that is, one day, was it like 1842 or something, 1840s, a man named Hamilton was walking down a river with his wife, and this realization came to him that he thought was so important that he engraved it into the bridge, and it's still there, or he carved it into the bridge. And so that realization was quaternions. Now, it didn't come as a bolt of lightning with no context whatsoever. It was he'd been thinking about it for like 10 years, and so the idea is, okay, you have complex numbers that encodes scaling and rotation on a two-dimensional surface. Well, can you then sort of upgrade that and do it in a three-dimensional space, right? I mean, that's kind of an obvious question. Once you decide that imaginary numbers are useful, then can you expand it? And he... Hamilton is considered a great mathematician and physicist. Those who study physics will have heard of if you study it in university or something, you will have heard of the Hamiltonian that's named after him. But anyway, so he worked on this for like 10 years, and finally the answer came to him. Now, the obvious thing to do, because complex numbers, they control scaling and rotation in 2 dimensions, and they have 2 parameters, because you have the imaginary number, the real number, and the imaginary number, right? So 2 parameters to sort of control 2 dimensions, if you will. And so the obvious thing to do is have 3 parameters. So let's add another imaginary unit, call it J or whatever. And so, yeah, have 3 parameters to control 3 dimensions is sort of the obvious thing to do. But that's not right. It actually turns out you need 4 parameters, not 3. And so I think that's why it took some time for us to realize, oh, there's this higher version of complex numbers. So yeah, it really is, and complex numbers sit inside of the quaternions. Okay? And so it really is a higher, I guess you could call it a super algebra, but that kind of has a specific different meaning. But it's the complex numbers form an algebra. That just means that it's a system where you can add things and you can multiply things. That's an algebra. And so the quaternion algebra is this larger algebra, and you have lots of little complex planes embedded inside. You can think of, I don't know if you've thought about rotation a lot, but typically we think of an axis and rotating about that axis. So imagine it like the Earth. If you want to define any kind of rotation, you need to define some axis, which you could define as a point on the Earth, a point on the sphere, and then you need some amount of rotation. And so when I'm thinking of 3-dimensional rotation, I'm imagining this sphere and maybe an axis that goes through it. And the axis, it has 2 points on the sphere. And so I'm sort of associating rotation in 3 dimensions with a sphere in some sense. And then, so each slice that you can do of the sphere, which is an infinite number of slices, each slice would define a 2-dimensional plane that it is itself a subalgebra of this quaternion algebra. Now, it turns out that there's you would need kind of two surfaces of the sphere. There's something called a double cover. So, and it's related to the fact that I just pointed out that if you have an axis of rotation, it touches the sphere in two parts. So it's sort of, you can think of it as being sort of double defined. There's for every let me think. So for every unique rotation, I think there's two quaternions that could define that. So that we call that a double cover. But anyway, so these complex planes that you could slice through it, they form this these sub-algebras, they're called. But anyway, so that's neat. So we've got this bigger quaternion structure. It has 4 parameters. So usually you have a real component, and then you have I, j, and k. Now, some people watching will say, okay, but you said that you described that as a revolution in math and physics, but other than like computer graphics, people aren't really using quaternions at all. If you have a degree, a bachelor's degree in physics or in math, in your day-to-day, in fact, I think some people go through that without really having learned quaternions at all. So, and almost no one in their day-to-day uses quaternions unless you're doing computer graphics. Even Roblox has quaternions, though they don't bother explaining them at all because that would be too difficult. The documentation mentions quaternions twice and makes no effort to explain them, which is funny because it's the most difficult thing in their docs for sure. But anyway, they just gave up on explaining those. But so going back, so I want to explain why this was a revolution. How? Because I think a lot of people will find that suspect. But it turns out basically that, yes, using quaternions is complicated and kind of too much in a lot of ways. It's hard to grapple with them and get a good intuitive understanding of them. They're difficult to work with, okay? But what ended up happening, to make a long story short, some clever individuals looked at the quaternion algebra and they extracted the useful bits. Well, they wanted to not bother with it so much. So they thought, how can we sort of make a simpler version of this, extract out the important parts, and then so we can forget about quaternions. And so they did that, and that is where you have the dot product and the cross product. The dot product and the cross product were directly extracted from the quaternion algebra. When you multiply two quaternions, you can sort of you view it as having these two separate parts. You have basically a dot product of the real parts. So there is a sort of, again, there's this analogy of rotation and scaling, but now it's in 3 dimensions. So a quaternion will, so a unit quaternion will just do a rotation, but a quaternion in general will rotate and scale. So if we say the norm of, basically the if you think of it as a vector, okay, the magnitude of the vector, don't worry if you're not understanding some of this terminology. We'll get back to the main story here in a second, but if the magnitude of this quaternion is 1, then it just does a rotation. And if the magnitude is greater, it also scales things out. And these are important things because, how I've said things up until now, you're probably thinking of manipulating objects, rotating and scaling objects. But you can think of it as rotating and scaling space itself, okay? So it's a bit more general than that. And that specific concept, what I just mentioned, basically, is the idea of passive and active transformations. I always forget which is which. Maybe the passive one. But anyway, you can think of these as transformations. You can think of transformations as being done on an object, or as affecting all of space in whatever system you're talking about, be it 2 dimensions, 3 dimensions, and so on. So that's true of transformations in general. They have this sort of the kind of duality here where you can think of it 2 different ways. And this is really important in computer graphics a lot. For example, and if you're making a game, you can think of the player moving around in the world, so the camera moves around in the world, or you think of the player, you think of the camera as being still, and the world moves around. And often, usually, with 3D, it's when you get into the nitty-gritty mathematical details, it's easier to have the camera fixed, and then the whole world moves around the camera. So I guess that's a passive transformation. But anyway, so yeah, there's this kind of duality. That's interesting, maybe important. I think it's important. Okay, so kind of rolling back here. The dot products and the cross products were extracted from the quaternion algebra. So yeah, if you can multiply 2 quaternions, the scaling, the magnitudes just work like a dot product. And then the other stuff in the quaternion basically works as a cross product. And so these useful things were extracted. And so I don't know if everybody studies dot products and cross products in high school. I did, but it definitely comes up in physics pretty early on, right? And they're used all the time as very basic things in electromagnetism, for example. But yeah, I mean the dot product and the cross product are just useful. Again, it's sort of extracted from the concept of 3 dimensions in a way. If you say that there's a connection between transformations of 3 dimensions and quaternions, then just making use of the transformations of 3 dimensions means that this, the quaternion algebra itself is useful, or these parts, the dot product and cross product, will be useful. So that's where we get the dot product and the cross product. So I would say that was a revolution, but it's not. And so that's a sort of a prerequisite for. There's more advanced things like vector calculus and all the stuff in an electromagnetism course. All the mathematics there. There's vector calculus, and this is sort of foundational. That I would say quaternions were something of a revolution, even though they were sort of, some people called them evil, and they were viewed as very complicated, so you had to sort of extract the useful parts. Now, sort of immediately, the question was raised, and I'm not going to go too much into the history, though it's quite interesting, but basically immediately the question was raised, well, can we do more? Like, what about 4 dimensions and so on? Because we had complex numbers for 2 dimensions and quaternions for 3 dimensions. Can we do something? Can we do more? And, well, it turns out, yes. Pretty quickly, somebody found out that you can have these things called octonions. And so the octonions are going to have 8 parameters. The complex numbers have 2 parameters. So let's go back. The real numbers a real number system is 1 parameter. Complex numbers are 2 parameters. Quaternions are 4 parameters. Octonions are 8 parameters. What's the pattern? The pattern is that these are powers of 2. And so, so octonions, so these were then studied, but there's a bit of a weird history there. The person who found it wasn't given credit right away and stuff like that. But focusing on the math here, people studied these things, and what happens, which is sort of interesting, is you actually lose properties as you generalize here. So as we generalize from real numbers to complex to quaternions to octonions, we lose properties. And so why would that be? Well, it makes sense that as you go to something more general, you lose properties. As you're more specific, you have more properties. And so going from real numbers to complex numbers, what do you lose? You actually lose a sense of things being well ordered. So the real numbers, we can order them, negative infinity to 0 to positive infinity, right? It's very obvious to order them. Now, when you talk about complex numbers, part of this is rotation, so you can imagine a clock. Well, it's easy to say 4 o'clock comes after 3 o'clock, but in a sense, 3 o'clock also comes after 4 because the clock comes back around. And so in some sense, you lose some sense of things being well ordered. And then when you go from complex numbers, I'm going to take a photo because my camera will die unless... there we go. When you go from complex numbers to the quaternions, you lose commutativity. So yeah, that's the idea that, AB equals BA, that it doesn't matter what order you do things in. For the ordinary numbers, real numbers, when you do algebra in high school, you learn, the distributive property, commutative property, associativity. There's one more I'm forgetting. But yeah, so you lose commutativity, and, rotations are not commutative. So I'm not going to go too much more into detail. Look that up if it's like, what is he talking about? Rotations aren't commutative. What does that even mean? Do a Google search. Ask AI or something. Anyway, then when you go from the quaternions to the octonions, you lose associativity. They have a weaker form of associativity, actually. I forget what it's called. But yeah, so you lose more properties. Now, can we go even further? Well, yes, you can. You can go to the sedenions, which are now 16 parameters. And you, again, lose something. What you lose, I'll refer to it as sort of losing inverses. So the thing is that you can take two non-zero sedenions, multiply them together, and get 0. So that's a little weird, because the numbers that we're used to, if you multiply two things together and you get 0, that means that one or both of them were 0, right? For sure. But with sedenions, that's not the case. So that's weird. So now I'm going to get a little hand wavy here, but obviously I cannot imagine 8 dimensions or 16 dimensions, but I imagine the Sedenian algebra as having this landscape and then these singularities of 0 points. There's some kind of geometry. So 0 is not just this one singular point. Well, maybe it is, but it has some kind of geometry associated with it where there's multiple ways to get to 0. And so this would break down. So if you tried to use this in physics, I think it would kind of break down the concept of the conservation of information. So conservation of information, I don't know if that's ever been put down as a formal law of physics or anything, but it's something that Leonard Susskind talks about. He's a famous physicist. Conservation of information. So, okay, so in this talk, we're going to get into physics at some point, but, you need to know that there's this huge elephant in the room with physics. There's this huge problem, and that is the problem of bringing gravity together with the rest of physics. So we basically have quantum physics and then gravity. And we have the only way we know how to bring them together, I guess, is string theory. But string theory, then when you go there, you have added baggage that comes with it. Like there needs to be, depending on the theory, there needs to be like 10 spatial dimensions or 11 or 14 or something like that. And then so they try to argue, well, there's all these extra dimensions, but they're just all wrapped up in a tiny space. So we don't have any actual evidence for string theory. The good thing about string theory is that it has managed to bring together gravity and the rest of physics as we know it. So you can say that different ways. You can say gravity and quantum physics, gravity, and particle physics, gravity and the standard model of physics. So it's often called the standard model of particle physics. That's our modern understanding. And it uses what is called quantum field theory. So when people say quantum mechanics, sometimes they just mean quantum physics. They mean the whole thing. But some physicists, when they say quantum mechanics, they mean the more elementary stuff like the Schrödinger equation. In contrast to the more modern theory, the modern version is quantum field theory. And the difference is that, or one of many differences is, well, with the older version of the theory, sort of normal class. I almost said classical quantum mechanics. Quantum mechanics. Okay, in its earlier form, you talk about, say, different, electrons as being different things. But in quantum field theory, there's just an electron field, and so the concept of an electron in the modern theory it's not like its own thing in a way. An electron is just an oscillation in the electron field. And so I think I've seen like Brian Greene explain things to Neil deGrasse Tyson by saying, well, the problem with the reasoning of what you're doing there, or what's implicit in your question, is that there's these separate electrons, but there's only one electron field. So anyway, so it has this modern version, quantum field theory. Okay, so we have this huge problem in physics, which is how do you bring gravity together with particle physics, and that is probably connected with just having some kind of theory of everything. But so sometimes people talk about this sort of almost interchangeably, and sometimes people view these as very separate things. There's the quest for the theory of everything, and then there's the quest for quantum gravity, which is just bringing together, mathematically bringing together quantum physics and gravity, because they use math that's very different, that is often described as oil and water, very difficult to bring it together. So we have this is the biggest problem in physics. It's often an analogy is made between this current problem and what we had before was the UV catastrophe. My channel might be named after that. I might have named myself after a catastrophe, but so UV catastrophe. So the ultraviolet catastrophe. I'm not going to explain it. It was something that was a problem, and figuring out the answer to that problem ushered in the revolution known as quantum physics. Okay, so can I remember how we got here? We've gone on a bit of a journey here, and I haven't even gotten into my math journey stuff here yet. This is all just setting the stage still, but we'll get there soon. So you can talk about octonions, you can talk about sedenions. You keep losing information. Now you can go further than sedenions. I don't know too much about what happens as you go further. I imagine, this is just a guess, that the geometry associated with the zero singularities changes. So that's, again, I think of sedenions as having these zero singularities with geometry around them. When I say singularities, I suppose it's just one. It's just zero, but it has some kind of geometry. Now, I'm very hand-wavy with this because I have not done a lot of work with sedenions. I've read some papers and stuff, but this geometry around the zero singularity is associated with this thing called G2, which is the automorphism group of octonions. We'll talk about it later. Okay, don't worry if that sounded like nonsense. But anyway, so what happens? I talked about how you can multiply two sedenions and get zero, even though those two sedenions were non-zero. I view this as conflicting with the idea in physics of conservation of information. And so that idea of conservation of information in particular is important to Leonard Susskind, and I associate it with... so he's studying what happens at the surface of black holes, because what happens at the surface of black holes is very important. Well, it's a way of tackling this this problem that I mentioned of bringing together gravity and particle physics. Okay, because in most areas of life that we can do experiments, you don't have the obvious impact of quantum mechanics and gravity also coming into play. Now, it's something of a misconception, sort of a common myth, that the quantum stuff is the world of the small, and gravity is the world of the big, and they're separate. And so some people have this cartoon idea of physics where the small world is, when we zoom in a lot, it's described by quantum mechanics. And then the big world of planets and stars and so on, that's described by gravity. And then in between, there's classical physics and, the ordinary Newtonian mechanics and stuff that people learn in Physics 101. And also electromagnetism and stuff like that, classical physics. And this is a cartoon image that's totally wrong. Because while in order to sort of extract the information of quantum physics, yes, we look at individual particles or two particles at a time, small little examples. But according to the theory, okay, you can talk about the quantum wave function of the sun. You can talk about the quantum wave function of the Earth. You can talk about the quantum wave function of the entire universe, or at least the entire observable universe, if not the entire universe. There's nothing in the laws that says, oh yeah, but this only happens in small areas, okay? So it applies, according to the modern theory, all right, it applies just as much to large objects as to small when we're talking about quantum physics. And gravity, an electron should have some amount of gravity associated with it, and a photon as well, because gravity, it turns out, a lot of people say when they write YouTube comments and stuff, they talk about mass associated with gravity, but it's energy. Mass is one type of energy, and so that's part of Einstein's general relativity, which is our modern theory of gravity. That it's actually energy which it creates gravity, if you will. It causes curvature of space-time. So it's not just mass, it's actually energy, and mass is one form of energy. Anyway, so yeah, we're getting on all these tangents, try to reel things back in here. There's this big problem of gravity and bringing together gravity and quantum physics. Researchers are looking at things like, or they it's hard to look at it, but things like the surface of a black hole, trying to figure out what the heck is going on there, is one way of trying to tackle this very difficult problem of bringing together the problem of quantum gravity. And you'd think, like, how can we possibly make any progress on that? Well, Stephen Hawking made some progress with that. I think he was maybe the first one to really make some progress there. So it's not a full unified theory of quantum gravity, but some progress was made using some interesting arguments. And so he came up with the idea of Hawking radiation, the idea that black holes radiate some kind of energy, and so they sort of very slowly dissolve, in a sense. They very slowly radiate energy away and get smaller and smaller. But it'll take many, many billions or maybe even trillions of years for these big black holes to fully dissolve. Dissolve, I don't know if that's the right word, but yeah. Dissipate. I think that's what I was looking for. So when Leonard Susskind, I think he calls it the zeroth law of physics, which is what he calls conservation of information. He's very focused on that, and he believes in it very strongly. And I'm saying if you try to do physics with Sedenians, maybe you're going to lose the conservation of information, because once you get you can get to zero and not know how you got there anymore. And so why would you even think of using Sedenians for physics? Actually, I mean, there's a paper, I'm sorry, I don't remember, but it's actually from some researchers in Wuhan, China, something about Sedenians and physics. If I remember, I'll put it in the description if I can find it. But okay, so going back a bit. So basically, complex numbers were found to be useful. We have the imaginary number I in the Schrödinger equation. Quaternions are useful because you can probably do electromagnetism with quaternions, okay? And also, I think you can do ordinary quantum mechanics with quaternions. Useful because they're useful for 3 dimensions, and the spatial world that we observe around us appears to have 3 dimensions. And as far as our experiments are concerned, we've never revealed anything more than 3 dimensions of space. So, yeah, quaternions can be very useful. So then the question is, what about the octonions? And this is where the journey begins. You can search for octonions on YouTube. You get some real interesting stuff. There's some lectures from a woman named Cole Fury that you'll find. They're very mysterious. And I think part of my journey was just seeing her lectures and then wanting to understand what the heck she's talking about, because it's like she's speaking another language that I didn't know. And now I've done a lot of study and I kind of understand her language now. But it's this whole world. So you get to the octonions, and I described the quaternions a bit, right? Sort of related to rotations, but it's actually this double cover of the space of rotations. And that whole thing, that whole bag, if you will, is basically the same as when people talk about spinors. You may have seen that. So there's another topic. You will go down a deep rabbit hole if you search for information on spinors. And so spinors are used to describe electrons. So basically, if I think of 2 electrons sort of approaching each other, and I want to think about, classically, they're constantly repelling each other. But in quantum physics, quantum mechanics, the way I think of it is, at each moment in time, they have a chance of exchanging a photon. And it's even maybe a little more complicated than that. There's something mysterious going on with superposition and entanglement. And then, okay, the way I think of it is that there's a cascade of information. And so if you have something, this is getting too deep, deeper than I wanted to go. But if you have a superposition, or let's say an entanglement of 2 electrons, for example, and you do an experiment on it. So you take a measurement. To me, there's this cascade, like this flow of information that originally they were entangled. The information was in superposition, and then there's this cascade of entanglement. Basically, to measure something is to entangle everything outside, is to entangle the measuring apparatus with the system that you're taking a measurement from. So there's this idea that measurement in quantum mechanics it's talked about quite a lot. It's pointed out as a problem because one of the interpretations of quantum mechanics, which is called the Copenhagen interpretation, is that there's this collapse of the wave function, but they don't really define measurement in that interpretation, and that's pointed out as a problem. But anyway, so I view measurement as this sort of, it's the measurement apparatus entangling with the system that's being studied. So anyway, if you're talking about two electrons, you can model them as spinors. It's this interaction of two spinors. But then if you want to get to the quantum field theory discussion, you actually have a field of spinors. It means that at every point in space, you have a spinor, essentially, that represents it. Just like if you have if you check the weather, they give you a map with wind speeds. There's arrows everywhere. That is the map with arrows everywhere. That's a vector field, right? I'm sort of blanking on the terminology. But and now, so each point in space has a vector associated with it. Now you replace each point with a spinor, for example, and then make it three-dimensional. So you have a field of spinors, and each spinor is probably a unit quaternion, I would think. And then there's this famous thing about these spinors and this thing called the Dirac belt trick. It's basically, electrons have this weird thing where if you rotate them by 360 degrees, well, I'll put it this way. In order to rotate an electron all the way around, 360 degrees is not enough. You have to rotate it around 720 degrees in order to get back to the original state. That's very strange. I could make several videos about spinors and the Dirac belt trick and rotating electrons and quaternions, and it's all great stuff, and maybe I will make those videos. But I want to get back to the story. So then there's this question of, can we use octonions for physics? And so this is a whole niche area. I would describe it as a competitor with string theory. I think it's very interesting. And here's why I think it's very interesting. Because I think that there's this question of, why do we live in three spatial dimensions and one dimension of time? I never really hear physicists or people ask this question. Why do we have three dimensions of space? And a possible answer, I believe, has to do with these, they're called division algebras. So the real numbers, complex numbers, quaternions, and octonions, they are algebras. Remember, you can add and multiply them. But they're called division algebras, meaning, and the division part there kind of means that you have an inverse. And so at the Sedenians, that's when that breaks down. You don't always have an inverse because you can get to zero in multiple different ways. You can get to zero and not know exactly how you got there, which is basically saying, yeah, I'll leave it at that. So these, and sometimes it's written RCHO, R for reals, C for complex, H is for Hamilton, which denotes the quaternions, and O is for octonions. So RCHO, that's the division algebras. Or sorry, the norm. It's the normed division algebras. Don't worry about that. I'll call them the division algebras. So this is an area of active research and very interesting, in my opinion. The question: are the octonions useful in describing physics? And I invite you to go look at Cole Fury. That's COHLFUREY. She has lectures up. But unfortunately, they're not meant for the layperson. They're meant for graduate level physicists. Okay, so they're very hard to understand, but she goes into it. And so I described sort of I mentioned some connections between electrons and quaternions, or that quaternions could be used to describe electrons. Now, when you get into the world of quarks and the strong force, things get a lot more complicated. And one way to try to tackle these complicated things is through studying symmetry. So basically, these things have symmetry properties. Okay, you can study quaternions and describe them in terms of symmetry. And the complicated bit there, I guess, is the belt trick. I actually think of it as a Klein bottle. So a Klein bottle is like a Mobius strip that you take it back and reconnect it to itself. I think the Klein bottle, but there's different types of Klein bottles, but the Klein bottle would have, I think, has this sort of Dirac belt trick thing going on. But anyway, so studying the symmetry properties of Klein bottles, these kinds of things are very interesting. And so at some point, symmetry became important in physics. We can go back to Emmy Noether, perhaps the greatest female mathematician of all time. And, well, I haven't sampled all of them, so I don't know, but sampled, that sounds wrong. But she's the one that sticks out in my mind, and for many. And then, but going also back to the development of what is called group theory. This is sort of the adult math way of studying symmetry, group theory. And then there's this thing called Lie theory, which is named after a mathematician named Sophus Lie, a Norwegian. And that's sort of the continuous version of group theory, more or less. And so they look at these things and try to describe them in terms of the symmetry properties. For example, look at the electron, and the photon, and the quark, and the neutrino, and all these things. And that's where you get that particle physics can be sort of neatly described as a combination of these symmetries, these Lie groups. So that's, in itself, super interesting. So all of particle physics, as I understand it, all of particle physics can be explained through this product of Lie groups. So it's U1, it's a U1 cross SU2 cross SU3. And I think you need 2 copies of that. And so what I just said potentially could describe all of particle physics. U1 cross SU2 cross SU3. Those are Lie groups. And we're multiplying them together, essentially. And that's very mysterious. That's already very mysterious. Now, Einstein, worked on unification physics, but he passed away before quark theory came into play. I think quark theory was like 1971 or so, and I think Einstein passed away probably like 1955, something like that. So he didn't have the advantage of knowing about quarks and the strong force. And I think I saw one quote from him. I think he was even a little bit slightly, he wasn't happy about the introduction of all this group theory terminology into physics. I mean, it actually turns out that Einstein, obviously a S-class physicist, okay, like among the best of the best, but not so much as a mathematician. I wouldn't describe him as a mathematician. I don't know that he really innovated anything in mathematics, except there's something called the Einstein notation, which is just a more convenient way of writing certain things. But I don't know. That's a good question. Maybe somebody out there knows. Did he do any innovation in math? I suppose. So when he had a lot of trouble actually going. When he wanted to create general relativity. So Einstein had this incredible year, 1905, where I think it was 4 incredible papers. One was the photoelectric effect, which I believe might have been when the concept of the photon was first introduced, and actually quanta, the word quanta from which is what quantum mechanics is about. I think those were introduced there. Basically, that's where he was. So again, back to the UV catastrophe, the ultraviolet catastrophe. Some research was done on that by I think it was a German named Max Planck, and he had some nice data and I think an equation that he came up with to explain the UV catastrophe, but he had no sort of reason for his formula. He just said, well, this matches the data, but it doesn't make any sense to me. And then Einstein came along and said, And by the way, these histories of physics, always take them with a huge grain of salt, because I'm hearing this from people. I watch a ton of lectures on this stuff, and physicists often are not good historians, unfortunately. So you have to be always take it. There's always, I think, these kind of convenient little stories that go along, okay, to explain things. But anyway, then Einstein came along and basically said, well, this data and this equation would make sense if energy were quantized. The light energy, the photon. So he introduced the concept of a photon. I don't think he used the word photon in that paper, but quanta of light maybe was said. So that was one paper. Another paper was, so he basically, he's not the only person important in the revolution that was quantum physics, but definitely played an important role. And then another paper, there's my camera, 1905, special relativity. That was a huge deal, right? I mean, showing that time and space are not absolute. They're relative, but there's another thing that is absolute called the space-time interval. So Einstein often was annoyed at how people described his theory. I think they may have associated it with like moral relativism and saying that, there's no absolute reality, everything's relative. But that's not really what it's saying. It's saying we have to replace the idea of absolute time and space with this other thing. All we have is this, the only thing we can agree on is this thing called a space-time interval. And it's basically altering the concept of distance and time, I guess, but there's a more, yeah. We can't go into the weeds too much here, but that was another paper. There's a couple other papers. I forget right now what they were, but I think it was definitely 3, but probably I think it was 4 big papers in 1905. But he realized with special relativity that there was some kind of problem with gravity that he started working on. And it took him 10 years to take his idea, which I believe was just, it's called the Einstein's equivalence principle. And by the way, there may be mistakes in this talk. Please leave a comment. Every time I talk for an hour, there's going to be a few mistakes. I might put it in the description or a comment. But anyway, so the Einstein's equivalence principle, he came up with that. It took a long time to get all the math for Einstein's gravity, which is called general theory of relativity, which is our modern theory of gravity. And it views space and time as bending. Okay, energy tells space-time how to bend. All right. And yeah. So I forget why I even started talking about that. So anyway, this business of octonion. Oh yeah, so Einstein didn't was not exposed to the quark model, and he may have not been happy about the introduction of, like, for example, Lie groups as describing all this stuff, because from his perspective at the time, it probably seemed like all this crazy terminology, like Lie theory, studying Lie groups, it's not trivial. It's usually a graduate level math course. Most people who study math in graduate school, I don't think study it, but a lot do. And it's very hard. Like there's at least 2, maybe more lecture series on YouTube where you get the full playlist of basically a graduate level course in Lie theory. And so imagine 10 or 15 lectures where it goes, here's an object, a thing, here's a proposition about it, or we can demonstrate that, here's a theorem about this, and then building off of that information, here's another object, and then here's a proposition and a theorem, and then built off that, there's another object. And go like that for 10 or 15 hours. That's a Lie theory course. It's hard, but great. And then the sort of crown jewel of a Lie theory course is the classification of Lie groups and the classification of Lie algebras. And so this is sort of the hardcore math way to explore the concept of continuous symmetry. And so we get into this concept of Dynkin diagrams. Dynkin diagrams are a way of representing Lie groups. And so, yeah, it's really cool that we can describe particle physics with these symmetries, these Lie groups, and or Lie algebras. There's a correspondence there. It's not exactly one-to-one. Lie groups, Lie algebras. And there's this other thing called Clifford algebras. And so there are people who study spinors. They found out about Lie groups. And then there's these things called Clifford algebras, which are nice big packages. So you can take the symmetry of the strong force of quarks, and then you can package it together with the symmetry of electromagnetism. You can package them together in a big Clifford algebra. And it'll have all these different types of spinors. There's actually more than one type. There's Weyl spinors and Dirac spinors. And some of the Dirac spinors factor in special relativity, if I recall correctly. But yeah, there's all this stuff. And now one thing though, so some people online think that the Clifford algebras are the ultimate thing. They're the ultimate package. You can bring all these things together, and it has this seeming promise of being unified and great. There's a YouTuber named Eigen Chris, who it's been a few months since I checked in, but he was doing a series on spinors and Clifford algebras. Clifford algebras. Fantastic, absolutely fantastic. And he's got playlists on general relativity, and the math associated with that is tensor calculus, this kind of stuff. But anyway, yeah, so he's got all that stuff. That's great. But a Clifford algebra will always be associative, and the octonion algebra is non-associative. In my view, the octonion algebra is more the big daddy. It's more general than the Clifford algebras, in my view. And also, Clifford algebras are used. There's endeavors to use it for programming graphics and games and that kind of stuff. And I've made a video about getting started with projective geometric algebra. So Clifford algebras are sometimes called geometric algebras. I view that terminology as the same. Some people say there's a distinction. I don't care, because people are using the terms interchangeably. And that's all very interesting. So going back a bit, quaternions were avoided for many decades because people thought, well, we can just use the dot product and the cross product. We don't want to deal with quaternions. It's a big headache. And then probably starting in the 80s, but more in the 90s, quaternions are very useful for computer graphics because you can interpolate rotations, meaning if you have an object with an orientation and you want to change it to a different orientation, different rotation, whatever, if you just use matrices, which are sort of the obvious sort of nuts and bolts thing to use, if you try to interpolate it, it won't just go straight over to the other orientation. It will do this. Usually, in general, it will have this sort of like wobble thing, like almost like, yeah, just kind of a wobble movement. And you can test this. Just take a 2D rotation matrix. It's like cosine, sine, negative sine, cosine. And so, for example, I don't want to get into the details too much here. Look up a rotation matrix and try to interpolate it linearly and watch what it does to an object. It rotates in a weird way. That's the point. So quaternions, if you want to smoothly, the word is interpolate, but smoothly transition from one orientation to another, just in the obvious direct way, you want to use a quaternion. It's computationally, that's the way to go. I can't think of anything else that you would do to interpolate that nicely. Incidentally, you can, for every one of these sort of rotations, there is the opposite way to go. You can go the long way around. And we said there's 2 quaternions. There's a double cover. There's 2 quaternions for every unique rotation. So there's going to be another direction to go. Interesting how math just works out at the end of the day, huh? Okay, so quaternions kind of came back in vogue a bit. They're still, complicated and takes a lot of work to try to wrap your head around them. And I have to confess, there have been moments of clarity where I'm like, yeah, I get it. Then I forget, and quaternions, every time I go back to them, they're a bit confusing. I gotta be honest with you. Non-intuitive, confusing. But kind of amazing. You feel like when you explore quaternions, you sort of feel like you're, exploring some kind of deep math. One way to explore them, if you want to, you can go into Blender and you can actually input. So you can start with a cube. You can find out how to just type in a quaternion and rotate the cube. That's a super nice way to do it. If you want me to make a video demonstrating that, just ask in the comments. Okay. So yeah, quaternions came back in vogue. I've just kind of gone all over the place. So people looked at these geometric algebras, often called Clifford algebras, and determined that, hey, we could actually use this as a nice, neat, big package to do a lot of things that we want to do in computer graphics and games. And in the middle here, okay, of this story at some point, there's this thing called a dual quaternion, and that's a very unfortunate name because I don't like that name at all. Because it's not dual in the sense that these sort of objects usually have a dual. It's some other meaning. Again, that's if you want. There's a talk about that on YouTube. I can leave a comment if you want it. But yeah, there was these things that they called dual quaternions that they were using, I think, for twisting objects neatly. And then, so but it's the way it's introduced is very confusing. It seems like just kind of comes out of the sky from nowhere. Here you can do this stuff, and magically you can twist things. And so then the geometric algebra is given as this way. I do think that if you can learn it and make use of it, it is the heavy machinery, the best way, the most elegant, sophisticated way to transform objects in 3D. If you want to do that for, again, graphics or games. But don't expect that anyone else is going to understand your code or what you're doing. If you're working completely alone and you want to do really hardcore math, but it's elegant, so you can take things that would be extremely hard to do normally, and you can do them very simply and elegantly. Once you equip yourself with this hardcore machinery and you have it in your brain, I've studied this stuff many times, and I don't fully understand it. I'm well on the road. And if you want to go even deeper in that direction, there's a Clifford algebra thing that's called conformal geometric algebra. And conformal transformations are related to sort of Mobius transformations and very important in physics. So that's a whole rabbit hole, hard to get into, very fascinating. I'd love to go down that rabbit hole, but we don't have all the time in the day. I mean, I'd love to study it myself. I don't mean I'm not equipped to explain it in more detail here. Okay, but all that stuff is well and good. But the octonions have something that all this stuff does not have. Clifford algebra, geometric algebra, whatever you want to call it, they're always associative. I'm pretty sure I'm not making a mistake here. I've studied this a bit. I think they're always associative. The octonions are not associative, so they have something going on that's different. Now, I like to think of... let's see. I'm trying to think how deep to go. When you talk about complex numbers... Let's talk about quaternions. I want to try to think of them in where a quaternion is described as a multiplication of two complex numbers, or sort of a composition of two of them. So you can sort of compose two complex numbers to get a quaternion, I think. And you can sort of compose two quaternions to get an octonion. That's how I want to think of octonions. And there's something weird going on here. So there's a guy I want you to know about named John Baez. He happens to be the cousin of Joan Baez. He's sometimes credited as having the first blog. I think he's a great mathematician. He teaches at UC Riverside, last time I checked. He's fairly famous in the math world. And he has a paper on, I believe it's something like octonions and the rolling ball. And so there's this way of thinking of octonions or describing. So what we want to do here with this, when you have some kind of complicated space and you want to describe it, you want to describe symmetry properties or transformation properties. You want to describe some way of, in your mind, moving around in the space or changing things or transforming things in a way that's intuitive to you. And so he uses a framework which he sort of inherited, he sort of built off of previous work, where you have a ball, and on top of that, you're rolling another ball. And these two balls have to have a ratio of the radii. I think, like, so basically the bigger ball needs to be like 3 times bigger or 4 times bigger or something than the smaller ball. Kind of mysterious. But there's obviously sort of symmetry things going on, because you can imagine rolling a ball down to, say, the equator, and then rolling it over here, and then rolling it back. And now this smaller ball, you've returned to the original position, but you've actually rotated it now. So it has some kind of rotational dynamics thing going on with here in the symmetry properties there. And going back a step, if you're talking about quaternion algebra, I think that you can map it to... When I say map it, yeah, you can sort of say, oh, this other thing is the same as this. So the quaternion algebra is basically the same as Mobius transformations. It's this world of complex functions. And complex functions, it's transforming the 2D complex plane into something else. It can transform in some weird ways. And that's conformal transformations, that's Mobius transformations. And so I think of it as, I think the quaternion algebra can be used to describe these Mobius transformations. So the Mobius transformations, this is mathematical jargon, I'm sorry, but for some of the audience this might be valuable. The Mobius transformations are isomorphic to SU2. SU2 is isomorphic to the quaternion algebra, and all of this is isomorphic to, I believe, the Lorentz transformations, which are used in special relativity. So you have these complex functions, which are cool. You can do Mobius transformations. It's very cool looking, and you can describe that with quaternions. You should be able to. And so somehow, when you go to the level of octonions, when you go up to this higher level, I try to think of it as the surface of these balls. You have these two balls, but the surfaces are complex planes. And maybe we have the total freedom maybe this is pure speculation and hand waving here, but maybe you have on both of these surfaces of the ball, you have the freedom of complex functions of Mobius transformations going on, and somehow they're relating in some kind of complicated ways. It's very difficult to understand. It's very complicated, but I invite you, if you're interested in it, John Baez's paper on the rolling ball. I believe maybe it's called G2 and the rolling ball, because G2 is the Lie group associated with octonions. Okay, it's called the automorphism group of the octonions. It's basically saying what are the transformation properties when you multiply octonions together, more or less. So, anyway, and then we haven't fully gotten into the rabbit hole here. We're 2/3 of the way deep. So this emergence of symmetry is very important. The study of Lie groups, trying to study and so there's the exceptional Lie groups, which I mentioned G2. It's called it's said that there's 5 exceptional Lie groups. G2 is the automorphism group of the octonions. So it turns out that these Lie groups sort of, or at least the Lie algebras, they sort of correspond to this discussion of the normed division algebras, RCHO, that we talked about before. So in Lie theory, there's not that many Lie groups, okay? But so you might be thinking like, oh, there's going to be thousands of them, and forget about studying them. But no, there's not that many, and but you can sort of draw this correspondence, like, oh, this Lie group is the same as the complex number algebra, and oh, this Lie group is the same as the quaternion algebra. So the symplectic group, it's called, that's a Lie group. The symplectic Lie group is the same as, isomorphic is the word, but it's basically equivalent to the quaternion algebra. There's something I was going to say. And that symplectic stuff is the same as the whole conversation about Heisenberg's uncertainty principle and the uncertain, like, there's sort of this trade-off in certainty between position and momentum. Okay, you can kind of relate that to, I don't know, symplectic algebra. There's this other thing called non-commutative algebra. I don't really know about it, but I think maybe it's using symplectic algebra as this sort of starting point to jump off of. I'm not too sure, but I think it's related to this stuff. Because you remember, the quaternions are not commutative, so I think that's where they get the name from. Maybe. And that's very difficult math. I mean, there's... there were professors... I think most professors will say, oh, non-commutative geometry. No, I have no idea about that. But anyway. So, yeah. This Lie theory stuff, which is used to describe particle physics, has some kind of, you can redescribe things in terms of RCHO, the normed division algebras. Very cool. And then this question of the Sedenians. So again, there's this paper out of Wuhan, Chinese researchers talking about using Sedenians. What I'm about to say is pure speculation. Maybe... So you lose the so-called conservation of information when you go to the Sedenians. But maybe if you take, for example, the many worlds interpretation of physics, if you take it seriously, perhaps the reality sort of depends on the observer. And the Sedenians could maybe give you a framework where you have different universes, different parallel universes. Basically that history, okay, when you make a measurement, I mean, Stephen Hawking in one of his books was describing quantum mechanics as sort of changing history, which is crazy. I mean, people. It's been said many times that quantum mechanics is very strange, and if you can imagine light bending around a black hole 2 different ways and then traveling 100 million light years to hit your eye, and when it hits your eye, it entangles with you, the information entangles with you, and then you find yourself in one of 2 universes, depending on how your eye measured the polarity of the light, for example. Weird. But so Stephen Hawking described it, and I think it's this is very contentious. I mean, somebody like Sabine Hossenfelder is probably, if they saw this, she would be cringing or something. But other people like Sean Carroll, okay, who I don't know if he still teaches at MIT. I think would be very open to these ideas. So Sean Carroll kind of is something of an advocate for the many worlds interpretation of quantum mechanics, which is growing in popularity. It's like maybe, I think when physicists are surveyed, it's roughly maybe a quarter, getting to be maybe a third of physicists who subscribe to the many worlds interpretation of physics. Now, whether you take it seriously or not, if you think it's a joke, that's fine, but there's nothing that we can point out that's mathematically wrong with that interpretation. And I think what a criticism that's frequently given about that interpretation is that it goes against Occam's razor. It makes things much more complicated. But the counter statement there is that the counterpoint is that actually mathematically it makes things simpler, not more complicated, because basically it takes the Schrödinger equation at its word. That's kind of how Sean Carroll describes it. That if you truly believe in the Schrödinger equation and the mathematics there, well, then you end up with many worlds. So Sedenians, I think, pure speculation, might be able to offer a larger mathematical framework where you have something like that. Okay, speculation finished. But I think it's interesting. And, the conservation of information, do black holes, if you went through a black hole, is information lost? And all this stuff is very interesting. Okay. Yeah, so trying to get to the deeper down the rabbit hole to get to where I want to get to, because it gets weirder, maybe. But these Lie groups can be described with Dynkin diagrams. They're just these little diagrams, simple diagrams, that describe these symmetries, okay? And now it turns out that there's 3 types in particular that are very important. And I think... so there are A, D, and E types. Just think of those as labels. It's not important right now. Yeah, those are fundamentally important. And so you can find all kinds of information about this online. If you search for ADE graphs, ADE Dynkin diagrams, ADE symmetry. Unfortunately, from my point of view, you often a bunch of string theory stuff comes up, and I'm always annoyed when I'm studying stuff and string theory stuff comes up, because the stuff I study does not require string theory at all. And so there are times when I feel I would need to understand string theory in order to understand what I'm reading, and I haven't really studied string theory very much yet. But so it's an annoying thing that happens from time to time with me is that I look for information online, and the only people talking about, well, the vast majority of the people talking about something I'm interested in are string theorists, and I don't really fully understand the language they're speaking, essentially. But anyway, so ADE graphs, ADE symmetry, ADE Dinkin diagrams. And so these are really fundamental and foundational. And then there's this thing called, we're going to, this is a lot. I know this is too much information. There's something called the geometric McKay correspondence, which says that these ADE symmetries relate to the Platonic solids. That is the symmetry of the tetrahedron, the cube, and the icosahedron. Okay, so there's 5 Platonic solids, and because of this thing called duality, I think it's called Poincare duality in this case, there's actually, they only describe 3 different symmetries. So the cube and the octahedron are duals of each other. They describe the same symmetries. The icosahedron and the dodecahedron are duals of each other. They describe the same symmetries. The tetrahedron is dual to itself. It's self-dual, so it describes one particular type of symmetry. So the tetrahedral symmetry is given the label A. The symmetry of the cube is D. And the symmetry of the icosahedron and dodecahedron is given the label E. Now, I'm mixing terminology from Lie theory and talking about Platonic solids. And again, it's the geometric McKay correspondence. Now, that correspondence is described in one particular way. I think there's deeper and more important ways to describe it, but I haven't figured that out yet. When I looked up the geometric, I have to keep saying the geometric McKay correspondence because there's a different McKay correspondence, which is extremely important in math. I guess this guy was important. So when I look up the rationale, the description of the geometric McKay correspondence, I'm always disappointed because I'm expecting some very deep, beautiful thing, and it's actually like very trivial and quick. But so I think they're deeper, more intuitive, more elegant, deeper explanations for that. So we have the symmetry of the tetrahedron. That's the A-type symmetry, A-type Lie algebra, A-type Dinkin diagram. We have D, and so D and okay, I'll talk about D first. But a lot of what I'm about to say is true for A as well. But D, so the symmetry of the cube, this D family, it's not just the cube, it's also the square. That's in 2 dimensions. And then you have a higher dimensional version of the cube, the 4-dimensional hypercube, sometimes called a tesseract. And we have the n-dimensional hypercubes, okay? Similarly with the tetrahedron, you can have, in 2 dimensions, you have a triangle. And then you can go up to higher dimensions. And it's called, for some reason, it's called a simplex instead of being called a hypertetrahedron. The n-simplex. And then so the A and D are these infinite families. So I think if you have a casual interest in math, you might already be interested in the symmetries that we're talking about. Symmetries of tetrahedron, symmetries of the cube or octahedron, and then trying to imagine the 4th dimension. There's a lot of tricks you can do to try to imagine the 4th dimension. And trying to think of hypercube is interesting, or hyperspheres also very interesting. That's another video topic. I spend a lot of time trying to think about 4-dimensional objects. And then, so now let's get to, so the A and D there's infinite families. They go on forever. You can always increase the dimensionality. The E family, this icosahedron and dodecahedron, I don't know if there's, 2 dimensions, maybe, I guess the pentagon. But they basically exist, there's 3 dimensions, and then there's 4 dimensions, and then it stops. It's not an infinite family. Now, I don't know exactly why. I couldn't explain to you why. I just I take mathematicians' word for it. I'd like to figure out a few explanations of why. Because I think there's a geometric reason, and then there's the Lie theoretic version, which is explained if you're talking about the Lie groups and Lie algebras. I mean, that's explained in every Lie theory course, I think. Why? So you have the 5 exceptional Lie groups, 5 exceptional Lie algebras, and it doesn't go further than that. I mean, that's that's a normal part of a Lie theory course. And then there are these sort of extended algebras and extended groups, I think they're called, which are described as tilde. So there's like a E tilde, which is, I think it's like if you just went a little bit further, then that's what we're talking about. And you go a little too far, and then things break down, and you actually don't have a proper Lie group, and so on. So, yeah, so it's interesting to me that, why don't we have a 5-dimensional analog of the dodecahedron or icosahedron? I can't explain that. It's very hard to think about 5 dimensions, but I'm sure there's a geometric explanation. I've looked a little bit online. I never found it. But yeah, again, I take mathematicians' word for it. So we have the icosahedron, the dodecahedron. So then in 4 dimensions, we have something special going on. So we've got, they're typically called the 120 cell and the 600 cell. The idea is that, I think the idea is like, if you go from the cube to the hypercube, so the cube has these 6 faces, which are squares, right? And the idea is that when you go to the hypercube, it's surrounded by, I think, 8 cubes, in a sense. And we call those 8 surrounding things cells. Just like, yeah, when you go... in 2 dimensions, the things surrounding on the outside, those are edges. When you go up to 3 dimensions, the things bordering everything on the outside, those are faces. When you go up to 4 dimensions, they're going to be cells. They might be cells in general for further n dimensions. I'm not 100% sure about that. So that's why they're called 120 cell and 600 cell. So the 4-dimensional analog of the icosahedron is the 600 cell, I think. And okay. So my mission recently is to understand. So again, the Lie, actually I didn't really properly explain this, but there's 5 exceptional Lie groups and Lie algebras. One of them is G2, we talked about. That's the automorphism group of the octonions. So it kind of somehow describes how octonions transform. There's another one, F2, I'll get to. And then there's E6, E7, E8. And I always forget which is which, but I think it's E6 is the complexification of G2, something like that. That sounds weird. There's a mathematician, I think his name is Vladimir Arnold. Vladimir? No, Vladimir Arnold. He mentions this. This is what, great mathematicians, they call it the complexification. I don't know what that means, but that's what they say. But actually, John Baez talks about this a bit. Kind of describes it. But, and then there's sort of the quaternionification, and then the octonionification, which is weird. I don't know. I could kind of try to make some kind of intuitive hand-wavy explanation, but it's probably kind of wrong, and it's a bit confusing and difficult. So I'm not sure if I should do that. But in some way, these exceptional groups are all related to the octonions, and the big daddy, the E8, the biggest one, is sometimes called the octonion group, I think it's called sometimes. And so roughly, this is related to projective geometry, and it has to do with, for example, I mean, basic projective geometry is used for game graphics, because you have to, if you're playing a game, it's on a two-dimensional screen, but we're representing a 3D world. You have to squash that 3D world onto a 2D screen. That's projection. That is an example of projective geometry. And so you can imagine using a vector, some vector operations to do that. Usually matrices are used, but you can imagine every point in space as corresponding to a vector. And so you're using a matrix multiplying times a vector to do that. And so I will give you my hand wavy explanation here, but this operation I just described of one example of projective geometry, this has nothing to do with complex numbers. It's just all real numbers. But there's something with projective geometry using complex numbers. And so I'll just be hand wavy because I don't have the machinery, the mathematical machinery in my head to properly explain this. But I think there's sort of a complex projective thing, and then there might be a quaternionic one, there might be an octonionic one. Some kind of projective thing going on. Sorry, it's hand wavy. I don't know. We're getting to the frontier of my knowledge here. But so there's the exceptional Lie algebras and Lie groups have something to do with octonions. That's the main point I want to make. But it's getting tired here. Whoa. An hour and 36 minutes. If you made it this far, give yourself a pat on the back. This is nuts. My brain is starting to turn to mush. It's starting to reach a limit here. But I wanna complete. I haven't even gotten to what I wanted to say here. Gotta get there. So, let's take a step back. ADE symmetries, okay? The E family is special, and so this E6, E7, E8. So E8 is the biggest, most difficult one to explore, to describe, and all that. So this E8 symmetry. So if you study Lie theory, you want to understand continuous symmetries, you want to understand spinors, and you want to understand the symmetry of the strong nuclear force and all this physics, and then you want to work on unification physics and the problem of quantum gravity, and you want to do all this crazy adventure stuff, okay? And so the E8 is the most complicated exceptional Lie group. So you're like, I want to understand E8. That's a very, very tall order. Now, E8, there's all this unification physics associated with E8. It actually caught the mainstream attention for a bit. I think it was, I don't know if it was in Time magazine or what, but I'm sure there's been many Scientific American articles and all this stuff. There's tons and tons of stuff out there, videos and everything you can find on E8 unification physics. So search it if you don't believe me. There's tons and tons of stuff. There are papers. And there's some criticism back and forth about if it actually makes sense. I could talk about why... No, I'm not qualified for this opinion, to have this opinion, but I think that it's a little too much, and there's reasons why... Well, actually, I don't want to speculate. But anyway, there's E8 unification physics, and it's the most complicated, crazy object out there. Just look at Google Images for E8. There's crazy stuff. It's crazy. So I have this mission to try to understand E8, and to try to understand how it relates to octonions, and to try to understand how it relates to the symmetry of the icosahedron. And that's a quest that's very difficult. And I did a lot of work on it last year. And it's been on the back burner in my head for 6-7 months. I occasionally think about it. Lately, I've gotten back into it a bit. And John Baez, again, has a paper called something about icosahedron and E8. Sort of trying to explain the connection here between the symmetry of the icosahedron and E8. Now, that paper is hard to understand, and he points out... It's a paper and a blog post, okay? Roughly the same information in both. But he tells a story, and then he says, you may have noticed there's a lot of gaps here, and you can find the answers to those gaps in the bibliography. So he has a bunch of references, and so I'm digging through the references, because that paper by itself is not enough to understand it. So this is all very mysterious. E8, the icosahedron, and it's not just the icosahedron, but it's the 4-dimensional analogs here. And again, you don't need both the dodecahedron and the icosahedron. You don't need both the 120 cell and the 600 cell. They have the same symmetry properties. So pick whichever one is convenient for whatever you're thinking about. And you can go back through my live streams on this channel. I've been playing around in Blender a lot and studying the dodecahedron, icosahedron, and studying how cubes fit inside of them. So cubes will fit inside of them. This is getting long-winded. I'm getting really tired, but I want to finish this. So 5 cubes will fit in a dodecahedron or icosahedron. So you have those. You have imagine a dodecahedron, and you've got these 5 cubes that fit inside of it neatly. And so I was wondering at some point, exactly how do we rotate from one of those cubes to the other? Can we rotate between them? And if so, how? And just playing around in Blender, I realized, yes, I think you can choose any axis of rotation that goes straight through the faces of the dodecahedron. Choose any of those. So there's 12 faces, but for every face there's an opposite face. And so you actually get only 6 axes. And you can, any of those axes, the numerology here is very interesting, because we're talking about 3 dimensions. We're talking about rotating a cube in 3 dimensions, and you can choose 6 different axes and use that to create 5 different cubes. It's very strange, because we're talking about a 5-fold symmetry interacting with a 6-fold symmetry interacting with a 3-fold symmetry, which is 3 dimensions, and all the symmetries associated with 3 dimensions. So it's almost like in 3-dimensional space there is a 5-fold symmetry sort of hidden away that you can unlock with the 6-fold symmetry of these 6 axes that you get from a dodecahedron. Now, instead of using the faces of the dodecahedron, you can use the vertices of the icosahedron. So you take an icosahedron, you connect the opposite vertices. There's 12 vertices in an icosahedron, so you get 6 lines. Each one of those lines is an axis of rotation. So I was thinking of it that way. However, so yeah, you can rotate this this cube along those axes. But I think there's something else that's more interesting. Instead of rotating it, transforming the cube, flipping it down and over in different ways is actually perhaps more interesting. And so I've been thinking about that, and I've been thinking of, instead of thinking of rotations here, each rotation is actually a composition of 2 reflections. So I've been thinking of breaking it down into reflections and trying to figure out, basically, I'm trying to think of this E-symmetry, or the symmetry of the icosahedron and dodecahedron, as describing ways to transform this cube. So it has this beautiful fivefold symmetry. Anyway, that's one part of this endeavor. And on Blender, I've been doing a lot of things programmatically making a icosahedron, programmatically making a dodecahedron, and so on, because I actually want to elevate this up to 4 dimensions, and I want to be making projections of the 120 cell and the 600 cell, and I'm sort of preparing myself for that. There's a whole other way to do it, which is using projective geometric algebra. If you go way back in my videos, I have an introduction to PGA. It's not actually an introduction to PGA. PGA, that's projective geometric algebra. It's a type of geometric algebra. It's a type of Clifford algebra, which is used, which exists. I don't know. It exists. But some people advocate it for computer graphics. So there's this cool thing, if you look online. I'm sorry, I forget his name at the moment. I actually interacted with him in a Discord server once, so I'm very happy about that. But there's a couple researchers who are sort of advocates of geometric algebra. And there's one demonstration of where you have, you can do a cube hanging by a rope, I guess, and have it sort of bouncing up and down. And you can, just by changing one number in the code, you can change it to a square attached to a string. You can change it to a tesseract, a four-dimensional hypercube attached to a string. Of course, it's going to be the projection. These are projections of, right? So we can't see four-dimensional objects. Actually, on a computer screen, you can't see three-dimensional objects either. So we're projecting the three-dimensional object onto a two-dimensional plane to see it. So if you want to try to examine a four-dimensional object, you can project it into 3 dimensions. Think of that as the shadow of the object, if you will. And then once it's a 3-dimensional object, then you project it onto the screen the normal way. So I want to investigate the 120 cell, the 600 cell, and so I eventually have to deal with projections of these objects. And one way is with PGA. It's hard. I've spent dozens of hours digging in. We'll get there. And another way is with Blender, just doing the math myself and everything. So ideally, I'd like to have both. I'd like to equip myself with both methods. But yeah, so this that's part of the motivation. Like, some people watching might be like, why is this guy so obsessed with making a icosahedron or a dodecahedron in Blender programmatically? Like, you're spending hours and hours and hours doing this. What the heck? Well, a big motivation is I'm preparing myself because I want to step it up to the 4-dimensional world, and I got to equip myself with some resources and abilities. I got to prepare myself a bit before diving into that fully. And so the motivation there is exploring these symmetries and, again, exploring the connections of the exceptional Lie groups / algebras with the world of the octonions, maybe even going up to Sedenians, but definitely octonions, and the world of these regular polytopes. That's in 3 dimensions, that's the platonic solids, but in full generality, they are called regular polytopes. So, very geometric story of regular polytopes, very algebraic story of the normed division algebras and E8 and so on, and then, or no, sorry, not E8, but just the normed division algebras and the Lie theoretics world. So I'll say it again: very geometric world with shapes, the algebraic world of octonions and so on, and then the Lie theoretic world. I want to, at least for myself, mentally bridge the gaps and be able to understand and possibly explain how all of these things are sort of elegantly connected. And John Baez, in his paper, he says he doesn't fully understand it either. So this is not This ain't no walk in the park, okay? But it's crazy interesting. And it's related with unification physics and all this amazing stuff. And there's one more thing I want to say here about E8. By the way, E8 has sort of a lattice representation, so I haven't mentioned about lattices, but the theory of lattices, if you look up stuff about lattices, you get a lot of chemistry stuff because it's important chemistry, but you can also study the theory of lattices, and that's another version of this sort of symmetry discussion. And sort of, you can think of functions on lattices, which they're often called modular forms in the two-dimensional case. A whole other can of worms related to number theory. It's a whole other rabbit hole. But it's very much connected to all this stuff. Then there's another thing I haven't mentioned, which is Coxeter systems, which is connected with the geometric aspect of this symmetry, but I thought I'll just mention it. Coxeter systems, Coxeter groups. But there's one last thing I want to mention, which is that it's a feeling or an intuition or something, and I probably would never say it publicly, except that it's the same thing is kind of said in this book I have. There's this book called Vertex Operator, Algebras, and the Monster. It's a crazy name of a book. The monster is this enormous finite group. I won't describe it. But anyway, so what I think is going on is that this E8 symmetry, the symmetry of the 120 cell, whatever, is telling us something about some kind of symmetry that traverses dimension. I mean, doesn't it make sense that when you're studying symmetries in n dimensions, there should be something that builds, like going from, say, 3 dimensions to 4 dimensions to 5 dimensions to 6 dimensions. There's some kind of symmetry that flows through something somewhere. I know that's super hand-wavy. But, I mean, the asymmetry, the d-symmetry, yes, there are these infinite families, but each, the 3-dimensional version, the 4-dimensional, 5-dimensional, they're all just their own thing. I mean, yes, the 5-dimensional hypercube has inside of it lots of 4-dimensional hypercubes, and inside of 4-dimensional hypercube, there's lots of cubes and so on. Yes. But I think there's something else out there. Some kind of symmetry, something that traverses dimensions. And a hint of that is that the golden ratio pops up everywhere when you start studying dodecahedron and icosahedron. The golden ratio is all over the place. And the golden ratio, when you square it, the golden ratio squared is the golden ratio plus 1. It's very strange. And if you keep doing that, if you keep squaring it, so you take the golden ratio plus 1, you square that, and then square that, and then square that, and so on. And you look at the coefficients of terms, because you're never going to get the golden ratio cubed, because the golden ratio squared is golden ratio plus 1. So the golden ratio cubed is going to be the golden ratio times the golden ratio plus 1. So you'll get golden ratio squared plus golden ratio, which again is golden ratio plus 1 plus golden ratio. So you get 2 golden ratio plus 1. And so as you do this process, you keep squaring and squaring and squaring. In the coefficients of the golden ratio and just the number, the Fibonacci sequence appears. And all of this has something to do with spirals. And you can look up, Mathologer has a bunch of videos about spirals, the most irrational number, which is phi, the golden ratio, and all this stuff. And it's related with continuous fractions and spirals and all this stuff. It's great. And so the number phi, the golden ratio, is readily present in when you make a dodecahedron or an icosahedron. If you look at the Blender live streams I did, you can see it in the code right there. I put it in. Or just look up how to construct a dodecahedron, how to construct an icosahedron. It's right there. So that's a hint. Somehow there's something weird going on. And I looked, before recording this, I looked a bit for my copy of the book, Vertex Operator Algebras and the Monster. But and that must be a somewhat famous book because it's in the local university library, I found out. So I'm like, oh, I was really surprised to see it. And there's a YouTuber who focuses on that book and just made a YouTube channel just like going through that book. I forget his name, though. Maybe I'll put it in the description. So it's somewhat of a famous book. I think it came out like 1988 or something, surprisingly, or 87 or something, surprisingly long ago. And it mentions something about that. It's mysterious. Yeah, I think there's... And maybe this is well understood by someone out there, and I'm just not finding the information. I would love it if somebody would point me in the right direction. I think there's some kind of symmetry or symmetries that traverses dimension somehow. I don't know how else to explain it. And I think hyperbolic geometry would play a role. Because when you study these, like projective geometric algebra, for example, you have this interesting idea of geometry the geometry at infinity. So you can imagine some kind of function that is transforming your space, and maybe it has a singularity at the origin, and then as it goes out to infinity, there's some kind of geometry at infinity. Anyway, that might sound like nonsense to you, but if you look up, I can direct you, if you leave a comment, where to find it. In the resources for PGA, for projective geometric algebra, this is kind of stuff that they talk about. This geometry at infinity. And it's a bit mysterious. And I think I'll go full speculative here, but it's not that speculative. So knot theory, this all has something to do with knot theory too, probably. So knot theory was shown to have this huge connection with quantum physics. And that was shown, I believe, in 1987, about 88 maybe. It even made like the cover of the Time magazine, or maybe New York Times, I forget. So it was Ed Witten that found it, but it was based on a talk from a great mathematician. I forget his name at the moment. And so, yeah, this enormous discovery was made about this connection between knot theory and all of quantum physics, essentially. That it seems that you can explain, or there's this great correspondence between them. And so I think in the 90s and early 2000s, a lot of physicists and mathematicians, well, a lot of physicists were looking for more stuff there, more maybe unification physics stuff. And John Baez, when you go to a lot of his older posts, because his blog is called the N Category Cafe, there's a lot of stuff about that. You can find stuff, John Baez knot theory. He has a lot of posts about it. And that's how I know from him, talking about how in the 90s and so on, people were really looking for more connections and stuff. Connections, tying the knot. But, and Conway worked on knot theory, and I'm sorry, I forget her name. There's this great female mathematician who worked on the kissing number of spheres in 8 dimensions. Was it her? No. I'm thinking. Sorry, there's someone different. No, it's someone different. Excuse me. There's a woman who has a talk on YouTube, something like exotic spheres in 4 dimensions, and she has also done some work on knot theory. So she proved something about a knot that Conway came up with. Something that Conway was working on, trying to prove, maybe a conjecture, and she proved it. Anyway, so knot theory is connected with this stuff as well. And there's a Japanese mathematician, I believe his name is Masanori. And he's Japanese, but his work is in English. And he talks about this correspondence between knot theory and number theory. I have his book. I don't understand it. I think I made a short about it, that this is the hardest book that I have. And yeah, so there seems to be a correspondence between quantum physics and knot theory, and there seems to be a correspondence between knot theory and number theory. Well, can we then bridge the gap between knot theory, between, let's say, octonions and knot theory, or quantum physics and number theory? That's what it's looking for. Can we further bridge that gap? So, I think that's an open question. I don't know. I haven't seen... I'm sure people have worked on this. I haven't seen anything, though. I'd love to see anything out there, if you find anything. People working on... Well, I'm sure there's some stuff, yeah. Making number theory work with physics, but... specifically using knot theory as tying the knot between the world of number theory and physics. I haven't seen anyone directly working on that, but I'm not really familiar with Ed Witten's work, and there's lots of stuff I'm not familiar with, so it might be out there. Yeah, and that might be it for now. So, so I'll go a little more speculative here. So I think that, when Einstein introduced wormholes, I think his idea was that particles are singularities. And you kind of see people talking about this way about electrons and stuff now, when you see stuff like, basically it was discovered that the mathematics of electrons and so forth, there's some kind of equivalence between that and wormholes. Or I suppose it's the entanglement of electrons and wormholes. And so I think there's an idea floating around here that, because like a high energy photon a gamma ray, can break apart into a electron and anti-electron pair, okay? And those two pairs, they have equal and opposite angular momentum and all this kind of stuff. One's antimatter, the other's matter. And I think there's an idea floating around, I can't be the only one, thinking these are two wormholes. And that maybe all of the elementary particles in physics are actually different types of wormholes. So I think that was sort of a motivation of why Einstein and Rosen in 1935, they wrote a paper on wormholes. They didn't call them wormholes, okay? But perhaps, if we're going to unify gravity and physics, perhaps the elementary particles are, in fact, different types of wormholes, black holes. And I've seen Leonard Susskind sort of slip, and refer to an electron as a black hole before. But anyway, what was I going to say? So an additional thing is that I need to learn a lot more about this. I only have surface. Well, so in Einstein's general relativity, I think that there's no inherent twisting of space-time. I think that you can have rotating coordinates, okay? But I don't think there's anything inherently in there about actual rotating? Yeah, I don't think there's anything about rotating or twisting space-time. But there's something called the Kerr metric, I think it's called, which is about rotating coordinate axes. But I think, and I could be wrong, but I think that rotating coordinate axes is different from inherent rotation of space-time itself. And I think that this sort of potentially missing component has maybe been part of the motivation for things like twister theory from Roger Penrose, and possibly loop quantum gravity, and maybe other things. That, yeah, sort of the idea that maybe some kind of twisting is missing there. Now, there's this thing called Einstein-Cartan theory, and so I think maybe, now this is speculation, I haven't really looked enough into this, maybe, Cartan, this great mathematician who he's the one who finally finished classifying Lie groups. Élie Cartan, I think he thought, he looked at Einstein's general relativity and thought that it's probably missing some kind of twisting. And I have a book, because Einstein and Cartan, they exchanged a lot of letters, and I have their letters, but it's a bit hard to understand, to be honest. And so I think maybe, though, he thought that was perhaps missing, and I think, again, I haven't properly looked at it. I don't have infinite time. I want to get to it. But Einstein-Cartan theory, I think, is taking general relativity and doing more of twisting and rotating. And maybe you probably need that if you're going to look at figuring out these, if you're going to try and think of elementary particles as being singularities in space-time and relating to knot theory, maybe space-time itself, when it forms a singularity, can get knotted up, and that different types of knots correspond to different elementary particles, and maybe different energy levels of electrons and so forth, angular momentum energy levels and so on. That's very speculative, but I think there's reasons. There's a lot of. It's not pure. Well, it's if I say it's not pure speculation, there's reasons for having these speculations, right, that I've described. And so that is another deep topic, I think, is knot theory and how it connects with physics, and can it relate to theories of gravity and unification physics and yada yada, number theory and so on. That's another topic. But lately I've been trying to, on a deeper level, understand E8. And I feel like I'm getting close. I put in a lot of work, and I might be getting close. In particular, understanding it from the lattice point of view seems more approachable. So, and going through the bibliography on John Baez's paper about the icosahedron and E8, going through those sources, reading them, and sometimes learning math is like learning a language. You have to, like Cole Fury's lectures, when I first saw them years ago, those were she was speaking a different language, and I had to put in hundreds of hours to study Lie theory and all the prerequisites of Lie theory and so on, to before I could understand the language she was speaking. And so what I'm saying is, it's not always a perfect linear path. Sometimes you casually read some source and you're not always, nobody understands 100% of everything that they're reading all the time, okay? And so you just, if I were learning Chinese or something, I'm sort of beginner level, so I can read a text and just pick out, oh, I understand this part, yay. Like this one sentence, small sentence, I get it, yay. You can do that kind of thing with math, actually. And, there's, out of my collection of math books, there's a few that I have a lot of trouble understanding, and I'll sometimes put it in front of me, and I'll be happy just to start making progress. Oh, that phrase, I understand that, which I didn't understand 6 months ago. And, oh, what's this phrase here? I've seen this a few times. Let me look it up. And then you go for a couple hours on some journey online because you looked up some weird phrase that you didn't know before. Or a lot of times you realize, oh, there's this big prerequisite that I have not studied. And so, gosh, I need to study algebraic topology or some subject. For example, if you wanted to get into knot theory and all this stuff, yes, it's part of algebraic topology. But I just bring that up because I think a lot of people studying math, the way you learn math in K through 12 and probably in college as well, is this very rigorous thing where it's always, you set up this perfect foundation and then you move to the next part and perfect foundation and you're sort of building and building and building. But at some point, if you are serious about it, you might need to take this deep dive and start viewing it as a language. And it seems to me that the really serious math people, you do both. You do both. You take a take a dive in the deep end and immerse yourself in things like you're immersing yourself in a language. But you also go back to your foundations and build things up piece by piece. Make sure that you understand. Part of the reason for understanding proofs, for example, is that not only, there's understanding a proof where, okay, I get that this proves this thing, so I 100% believe this thing. And then there's understanding an intuitive sort of perception of the thing. So where you can quickly look back and see something intuitive, and you can see that this thing has to be true. That this theorem, for example, it's true because you rotate this object in your mind, and there it is. Like, you see, there's knowing that something's true because you've proven it through all these long algebraic steps, and it must be true. And then there's sort of perceiving that something must be true. That's more intuitive. That's what I'm trying to say. But so do both if you're serious about this stuff. And if you got to this far, you might be serious about it. I think that's it. I mean, the big mysterious thing to me is that what I said about this E-type symmetry may be encoding some kind of information that traverses dimensions. In other words, I'll give an analogy here, which is there's many cases where you get a little bit of machinery and it unlocks all kinds of things. You get the keys to the car and you can drive all over the place, and it's a whole new world for you. So, for example, you learn how to use matrices. And, that little 2D rotation matrix, cosine, sine, negative sine, cosine, you can easily embed that in a 4-dimensional matrix. You can use that as a building block and do a 6-dimensional matrix. And look, Ma, I know how to rotate something in 6 dimensions because the 2-dimensional thing was this building block. It was the key to the car. And rotating things in 4 dimensions and higher is a little weird because what is it? Like, there's these in 4 dimensions you can have 2 orthogonal rotations that just don't affect each other at all, whereas in 3 dimensions that we're used to, there are no orthogonal rotations. You're kind of stuck in this algebra, so to speak. I don't know if I'm properly explaining what I'm trying to say, but because a rotation, it is a kind of swapping, or it's some kind of thing happening in between two dimensions, right? So no matter what rotation you do in 3 dimensions, you can choose an axis. And so there's actually sort of a plane of rotation. There's always, for every rotation in 3 dimensions, there is one plane of rotation. But when you go up to 4 dimensions, you can have 2 orthogonal planes of rotation. And that's hard for us to imagine because we have trouble imagining 4 dimensions. And if you go up into 5 dimensions, you can have these, totally orthogonal rotations. So it's weird. But so I'm saying you can have, like, if you learn how to rotate, how to do this cosine sine trick with the matrix rotation, and you can kind of unlock, oh, now I know how to mathematically rotate things in higher dimensions with a matrix if I want to. And similar, this E-symmetry might have something that's unlocking something that then can be used in higher dimensional contexts. That's an attempt at an analogy of what I'm... and I have felt this, and then after I feel this kind of thing, it could be wrong, of course, but then I read something about that in this vertex algebra operators in the monster, and they're kind of saying a similar thing. I don't know if man, if the human species has fully understood E8 symmetry and everything that's going on with it. I think that a lot of mathematicians would agree with me on that. But who knows? There might be some incredible person out there who says, oh, E8 is easy, it's simple. I know, I totally get it. It's trivial. I think that person's probably arrogant. But anyway, I'll also mention there's, Norman Wildberger is a mathematician, I think, from Australia. Lots of videos on YouTube, and his paid content, he gets into, there's another, because these symmetries are going to happen in billions of contexts, okay? They're everywhere. So, and why is that? Well, I think that information itself can always be sort of decomposed into a composition of symmetry and asymmetry. If you imagine a grid, let's say 8 by 8 pixels, okay, and the pixel is either on or off, and you just make it randomly on and off. I can send that data to you in 64 bits, okay, but I can compress that data by analyzing it for a axis of maximal symmetry, and then all the information compose it into symmetry and anti-symmetry. Yeah. Look at there's these puzzles called nanograms. Look at that kind of stuff. And if you do these puzzles, you realize there's symmetries. Like you can have vertical symmetry, horizontal symmetry, you can have diagonal symmetry, right? And you could imagine also in some cases you could have like a skew oblique, sort of an oblique symmetry that's not an exact 45-degree angle. And these nanograms are called Japanese puzzles as well. Very interesting. And so you have all these... So yeah, I think the information itself can be decomposed into a composition of symmetry and asymmetry. So I think that's why you kind of see it everywhere. And anyway, so Wildberger, he has a way of tackling these this Lie theory stuff. I believe he was basically a Lie theorist. I think he did his PhD in Lie theoretic stuff. But I think he's been a professor for decades. And there's this stuff with population games on certain what do you call it? On graphs, actually. So yeah, I'll just mention it because that's another way to tackle this stuff that is very interesting. Population games on graphs. Norman Wildberger. He has a few talks on that are free, but he has paid content. It's good stuff. Why not support it? Obviously, this is not sponsored or anything. I've never spoken to him, but yeah, populations on graphs. That's another place where these symmetries manifest very interestingly. I suspect that they manifest in these nonogram puzzles that I was mentioning. So there's this on Switch. I don't know if it's so. I'm in Japan. I'm not sure if you have it in the West, but there's a game called Pixel Cross, which is in the Super Nintendo collection. And I think I'm still looking for the E-symmetry in the nonograms. And that also is actually, there's an area of study called tomography, discrete tomography. It's related to MRIs, for example. They scan something and the computer has to basically kind of do something very similar to these Japanese puzzles. They're sometimes called Japanese puzzles. By the way, it was invented, I think, like 1987. I keep saying these things are invented 1987. That's when I was born, so I might be off by a year or two there. But yeah, Japanese puzzles, very interesting. And do they have E-symmetry? I'd love to know. You can kind of make what looks like a quantum bit in the puzzle. I'll show you real quick. This nonogram, this Japanese puzzle. Hold on. Let me focus this. This very simple puzzle kind of acts like a qubit, because it has either of the diagonals, so it can either be this diagonal and this diagonal, or this diagonal and this diagonal. And if you had this grid attached to other things in the nonogram, I think there's ways of treating this like a qubit, and you can set the bit and it would cause sort of a cascade of information. You could probably, I feel like you can build circuits and maybe, I don't know about all of the quantum circuits and quantum logic gates and that kind of stuff, but I think it's something I work on sometimes. Very interesting. And I'll also mention that a vector space, you have a weird vector space. I'll try to draw here, different from the normal one. So imagine like the same grid we just did, but imagine I just made it a little bit 3D. So above this grid, you have another copy of the grid, and if I fill in one of these pixels like this, then that's hard to explain. Okay, I'll represent that in this three-dimensional picture. So 3 of these pixels are off, and 3 of them are on. So I'll represent the top part of this cube as being filled in because they're off, and then the bottom part is on. So the bottom part has one of them on, and the other ones are off. So they're filled in above. So actually, I have a Rubik's cube talking like this, and then so if one of the bits is on, we have this voxel now. It's a 3-dimensional pixel. It's a voxel. This is now on, and then the other ones are off. So these will be switched on here, but in the off position. And this sort of forms a little vector space mod 2, I guess, somehow. I mean, but yeah, you know, vector space mod 2, I think they usually say characteristic 2 is a little, something I think about a bit. It's a little strange. And probably relates to computer science because, you know, you have bits and ones and zeros all over the place. The D symmetry, you know, the symmetry of the cube relates to bit flipping. Okay, if you have 3 bits, so let's start at 0, 0, 0, and you start flipping bits, you can imagine you're moving around on a cube. You flip all the bits, you're on the opposite side of the cube. And you can, so if you have 4 bits, you can imagine yourself moving around on a hypercube. Each movement along an edge is a flipping of 1 bit. I'm not sure how to think of the tetrahedral symmetry, the asymmetry in this kind of context. I think I recorded a video, and I'm not sure if I made it public. And then, but maybe permutations though with the asymmetry. Maybe it relates to permutations. I don't know. So yeah, that's another thing. So I think I can find the A and D symmetries in the nonograms, but I haven't really found the E symmetry. But if you treat this thing like a qubit, and by the way, I mean, you have a D symmetry, a cube symmetry, because you have the, I just showed you a cube. Can you make it into a hypercube symmetry by treating these like bits and just connecting a grid of 4 of them? I think so. I think that works. Can you then expand that further to 5 dimensions? Probably. I haven't really thought about it. And then, yeah, the E symmetry. Anyway. But then, okay, so Wildberger has these population games on graphs where each node on a graph, each vertex, each point has a population associated with it, and you play certain population games. I don't think he's the one who came up with it at first, but some people came up with it. And it turns out that you have ADE symmetry appearing, and you can go to these E, like for example the E tilde transformation, and demonstrate that I think that it's not stable is the idea. So at some point the E tilde symmetry should break down. That would be probably like, going back to the geometric Mackay correspondence, I guess that's like trying to build an icosahedron in 5 dimensions and finding that it doesn't work. Something like that, maybe. Lots of mysteries here, lots of weird connections. And so you can see that I feel I'm in this ocean of math and physics and deep down the rabbit hole. I love it. It's complicated. There's lots of stuff to study. Leave comments with your thoughts. Peace out. I hope you have a great day. Bye.